India has different types of land and water conditions, from flat plains to somewhat dry areas, making it a unique challenge for managing water sustainably. Our goal with this research is to understand how groundwater behaves in this specific region and identify any patterns or trends. Going into the methodology, we have adopted in this study GRACE data with a monthly resolution at 0.5 degree was obtained from NASA Earth data. The GLDA soil moisture and plant canopy surface water products with a monthly resolution at 0.25 degree were acquired from NASA Earth data. In situ well data for the states were gathered from the WRIS website. The land cover map for the study area was taken from ISAR-CCI, while the biomap was obtained from USDA and RCS. The aquifer map was downloaded from the WRIS India website using the provided URL. Major aquifers were then extracted using QGIS and exported as PNG files. Coming to the methodology, to address the data gaps in GRACE total water storage, we filled them by extracting seasonality. The GLDA, soil moisture and plant canopy surface water products were resized to 0.5 degrees. Groundwater was estimated using these equations. In addition, in situ well data from WRIS India was collected and interpolated to 0.25 degrees using ordinary kriging. Trend maps for both GRACE, GLDAS and in situ derived groundwater were created in MATLAB, covering a 20-year period starting from 2002 to 2022. The correlation between these trends were then calculated. Subsequently, we are developing an LSTM model to predict monthly in situ groundwater based on the relationship between GRACE and in situ derived groundwater. This slide shows the methodology flowchart. Thus, derived groundwater trends are explained on the basis of land cover, biome and aquifer types of the study area. We are in the initial stages of developing the LSTM model. Coming to the results. The figure on the right shows the pixel-wise groundwater trend map derived from the GRACE and GLDAS. The table shows the hotspots identified. Cities like Meerut and Bijnor in UP show a negative trend of 7.1 cm per year, whereas certain places in central UP and east of Rajasthan have a negative slope of around 4.2 cm per year. Also, Delhi with a decline of 3.9 cm per year is among the states facing severe groundwater depletion. A pixel-wise trend map of in situ derived groundwater was also generated, which shows a high positive correlation of 0.99 with the satellite derived trend map. We can find the following types of biome with their distinct characteristics in our study area. First, desert temperate. Here, the groundwater levels are shallow or sometimes non-existent. Then, semi-arid temperate. This type experiences moderate groundwater levels. During periods of high rainfall, recharge may occur, leading to increased groundwater levels, whereas during dry periods, the levels decline. The third type of biome found is humid temperate. In this environment, groundwater levels are deeper and there is a potential for maintaining groundwater storage over time. Analyzing the groundwater patterns and biome types, we can conclude that heightened human activities, particularly the excessive withdrawal of groundwater without allowing adequate time for replenishment, have imposed substantial strain on groundwater resources. This strain is evident even in regions anticipated to have ample groundwater. The land cover in the study area exhibits diverse characteristics. Cropland, constituting a significant portion, faces the risk of depleting groundwater due to intensive irrigation practices and over-extraction. Deciduous shrubland, while contributing to increased evaporation, tends to reduce recharge, impacting groundwater levels. Urban areas with impervious surfaces hindering infiltration contribute to a decline in groundwater levels. Areas with broad-leaved trees play a positive role by reducing evaporation and enhancing groundwater recharge. Water bodies such as lakes, ponds and reservoirs serve as vital recharge zones, replenishing aquifers. The overall scenario indicates that the increased cultivation of water-intensive crops and urbanization, coupled with the insufficient presence of broad-leaved trees and water bodies, stands as a significant factor in the depletion of groundwater in the region. In the northwestern region, groundwater comes from different types of aquifers. Alluvial aquifers are widespread, particularly in the fertile Gangetic plains of UP, serving as a vital source of groundwater. Unconsolidated sedimentary aquifers are located in various parts of the northwestern region. In the Terai region, sedimentary formations with sand, silt and clay exhibit varying permeability in storage capacities depending on the specific characteristics of the sediments. Fractured rock aquifers can be found in hilly and mountainous areas of the study area. These diverse aquifers contribute to the availability and characteristics of groundwater in this part of India. In conclusion, it can be said that the declining groundwater trend, evident in both satellite and in situ observations across the study area, underscores the need for immediate remedial actions. A detailed analysis of land cover, biome and aquifer maps reveal that human activities, specifically over-extraction of groundwater for agriculture and water-intensive crops, are the primary contributors to this trend, hindering natural recharge and causing shortages even in areas expected to have abundant groundwater. We are extending this work by developing an LSTM model for predicting monthly in situ values using GRACE and in situ data. It has achieved an R-squared value of 0.9 as on date. These are the literature referred for the study. We would like to thank the authors and the organizers of InGARSS 2023 for giving us an opportunity to present this work. Thank you.
We are going to the second presentation by Surya, Prakash, Tiwari, or any author of this presentation. So is there any author of this presentation, either in the room or online?
I am Abdul Azeez, working as a research scientist at the Applied Research Center for Environment and Marine Studies, King Fahd University of Petroleum and Minerals, Saudi Arabia. Today, I am going to take a topic on an evaluation of machine learning techniques for retrieval of chlorophyll in open and coastal waters. Coming to the introduction, we all know about the chlorophyll, which is a crucial parameter for understanding the trophic state of ocean and land waters, which is strongly related to the biomass and the phytoplankton abundance. This phytoplankton converts solar energy into organic matter and contribute to the oxygen balance. These chlorophyll levels vary depends on the changes in the nutrient levels, environmental conditions, and also it changes seasonally. Monitoring chlorophyll concentration is essential for the evaluation of aquatic ecosystems. There are some traditional and remote sensing methods for analyzing the chlorophyll concentration. Traditional methods which involves the laboratory experiments and the in situ measurements, and also which is limited to the region analysis and costly, time consuming. Even though in the very rough conditions, the sea rough conditions, we cannot do the in situ measurements. So during that time, we can only concentrate on the retrieval of chlorophyll using satellite images. So you can see in the right side, the natural color and the chlorophyll concentration retrieved from the CWIF project. And you can see a big patch of chlorophyll concentration in the Arabian Sea. And this ocean color remote sensing plays a major role in monitoring water quality changes with efficiency. And there are some bio-optical algorithms for the chlorophyll estimation from the remote sensing reflectance. And we can use various ocean color satellite imageries for the retrieval of the chlorophyll. And also we can use some machine learning approaches. The recent studies use machine learning techniques for retrieving the chlorophyll. We can use multi-band combinations for retrieving the chlorophyll. And also there are some challenges in the chlorophyll retrieval in terms of the cloud cover in the satellite imageries. And if we combine machine learning approaches with the satellite images, then we can accurately extract the chlorophyll from the satellite images. In this study, the objectives are build and evaluate different machine learning approaches for chlorophyll concentration retrieval and also analyze the outcomes for single band and a multi-band combination of variables. This study, the data sets are used like normal data resulted in 589 remote sensing reflectance data and corresponding to the chlorophyll data for 5 different bands like 443, 490, 555, and 660 nanometer. And this data split into for training with a 300 combinations of bands, and for the validation we have used 289 combinations, and which is covering a wide variety of waters. And also we have downloaded mainly Sentinel-2 A and B satellite images with a spatial resolution of 10 meter and 30 meter resolution. And these images are level 1 imageries. And we have used the accurate software for the atmospheric corrections mainly. So coming to the methodology, we can say like the first thing is data acquisition, and the second thing is the pre-processing, and we can also use the algorithm the application of algorithms like in this study we have used SVR model, RFR model, and GBR models, and we can use in situ data sets for the validation of the chlorophyll with respect to these three models, and finally the chlorophyll concentration estimation from the satellite images. Now coming to the machine learning approaches, you can see we have used SVR, RFR, and GBR methods, and which utilizes SVR utilizes exponential intensive loss function radial basis canal function. RFR employs bootstrap and aggregation limit overfitting. GBR construct ensembles for decision tree models using boosting approaches. So after extracting the chlorophyll from using these machine learning approaches, we have performed the statistical analysis for the comparison between the in situ data and the the chlorophyll retrieved from the machine learning methods. Now you can see the comparison of machine learning models for chlorophyll concentration analysis. You can see three scatter plots of SVR and RFR and GBR. From these model matrices, we can see like GBR has a lower RMSE and MRE compared to other models, and you can see GBR have an MRE of 0.16 and RMSE of approximately 0.58 and with a correlation of 0.94. So in this study, we selected GBR for further analysis. So now we can we applied these GBR models to level 2 satellite Sentinel-2 imageries for the spatial distribution of chlorophyll in coastal waters, Al-Jubail, Saudi Arabia. So we have utilized the Accolade platform for the atmospheric corrections, and these images covering from October and November 2017. So from this chlorophyll retrieval, we can see like that the inland region, the chlorophyll values exceeding 1.5 milligram per meter cube, and in the coastal waters, it is ranging between 0.8 to 1.5 milligram per meter cube, and in the offshore waters, it is less than 0.8 milligram per meter cube. So overall, the satellite chlorophyll predictions align closely to the in situ observations, and also the values are within the expected ranges. And these methods we can use for long-term analysis of chlorophyll concentration in the coastal water. So we have analyzed a single session at Al-Jubail. We have downloaded the Sentinel-2 imageries from 2017 to 2020 and extracted the chlorophyll concentrations. And you can see from this time series analysis, there is an increasing trend in chlorophyll concentration at the end of November 2017, and which reaching a maximum of 1.9 milligram per meter cube. And the average concentration observed for this study is 0.9 milligram per meter cube. And there is no significant deviations of trend we observed from 2018 to 2021. But even though we have analyzed some seasonal patterns in chlorophyll values. So if we are downloading like more multiple satellite imageries, and if we use these machine learning approaches combined with the satellite retrieval of chlorophylls, and also if we do some atmospheric corrections with the supporting software like Accolade or other softwares, we can extract the chlorophyll concentration changes in the coastal waters or the inland waters, and which will provide a better accuracy. Coming to the conclusion from the study, we can say like that if we use effective machine learning models for aquatic remote sensing, we can study the long-term analysis of chlorophyll concentration, how which is behaving with respect to the season, or is there any bloom patterns. So we can use these machine learning techniques such as SVR or RFR or GBR or whatever it is So in this study, we analyzed that GBR performs well compared to other models. So we can use these machine learning techniques for the future studies. And these are the reference used for this study. And thank you. Now the platform is open for the questions.
So, sir, from your study, the monitoring chlorophyll content, I can understand, but can you just elaborate the retrieval part of the chlorophyll?
So we have used the GBR and SVR and RFR methods. That is a machine learning approach. We have utilized the Python packages for the for this. And actually, we downloaded the Sentinel-2 datasets and also CWIF datasets. So utilizing CWIF datasets, we found some band combinations, like in which band the chlorophyll concentration is lying. So like that, we have found some band combinations, almost 589 band combinations we performed. So using that method, in which pixel the chlorophyll is coming. So we correlated this with the CWIF datasets initially. So in that way, we have performed the chlorophyll extraction.
Okay, sir, but I was asking for the retrieval part, how we can actually retrieve the amount of chlorophyll or...
Yeah. There is a like OCM algorithm for retrieval of chlorophyll. So you can use the Accolade software that is freely available. Accolade software. So using that Accolade software, we perform the atmospheric correction. Then after that, in that Accolade software, there is a OC for algorithm is there. So using that, we can extract the chlorophyll.
Out of curiosity, I'm not a specialist in chlorophyll retrievals over ocean, but why did you use Sentinel-2 and not Sentinel-3 data?
So Sentinel-2, it is a high resolution data sets for the coastal water city, 10-meter resolution is there. That's why we have used the Sentinel-2 data sets.
Okay, so it's about resolution that you need, because I saw Sentinel-3 is better in terms of radiometry and gives you more observations, but you were aiming at resolution.
Yes, because in coastal waters, we have aimed for the resolution.
Okay, thank you.
Yeah.
No, very quick question. So if I understood well, you did not measure chlorophyll, but you use acolyte to retrieve chlorophyll, and then you trained the machine learning to give the same result of acolyte. Is that correct?
Yes, same result for the acolyte. Then after that, finally, we have one observation station at the Jubail. So we have performed the correlation analysis.
All right, but you have no validation for the acolyte result?
No.
I think we have to move to the next speaker. Thank you for the nice presentation.
Yeah,
the next
thank
speaker is Aparna R or Chandrakanta Ojha. Hope I spelled the name correctly. And this is also an online presentation. Are you online? The presentation is on SBAS INSAR analysis of coastal subsidence in Kerala. None of them is online? No, then we go to the next presentation. Okay, then the next presentation is on flood hazards mapping using GIS enhanced multi-criteria decision analysis in Kushalnagara, Taluk, India. Is the speaker? Yes.
Hello all, today I am here to present on flood hazard mapping using GIS enhanced multi-criteria decision analysis in Kushalnagar Taluk, India. I am Pavitra BS, MTech student from the National Institute of Engineering, Mysore. Flood hazard mapping is crucial for assessing and mitigating the risk posed by flooding events. It enables informed land use planning, emergency response preparedness, and infrastructure development in vulnerable areas. By identifying flood-prone zones, these maps contribute to minimizing the impact of floods on communities and promoting sustainable development, and it would help for environmental sustainability. Thus, for monitoring, this multi-criteria decision analysis plays an important role in integrating hazard, exposure, and vulnerability can be considered. The objective of the study is to evaluate flood hazard map using raster analysis techniques and analytical hierarchy process using GIS enhanced technique. Thus, Kushalnagar is a city located in Kodagu district. It is situated on the banks of river Kaveri. This area covers about 33 km square and the elevation is 844 meter. The latitude and longitude of this area is 12.47 degree north and 75.97 degree east respectively. This town is generally flat, although few areas are hilly. It has a history of flooding, helping us to understand and address the local flood risks, and the region's topography, land use, and rainfall patterns make it representative area for studying flood phenomena. Using SRTM-DEM 30-meter resolution map, the influencing factors or criteria like slope, drainage density, flow length, and land use land cover maps were generated by using spatial analysis tool. Using GIS techniques, precipitation and soil maps were generated by using the IMD gridded data and National Bureau of Soil Survey and Land Use Planning data respectively. Using SATI's 1 to 9 scale in analytical hierarchy process to assign weights and thematic layers of each criteria classes and assess their relative relevance. By allocating weights, the preference of each thematic layer in relation to the other thematic layer on the choice of flood-prone area delineation was communicated. This was accomplished by utilizing related review literature and expert judgment to populate a pairwise comparison matrix from which the set of weights known as eigenvectors as well as consistency ratios. The weightage is given for that respective criteria classes are 33.3, 12.1, 15.9, 12.8, 7, 3.7 and 2%. By using all this data, flood hazard map was generated using GIS techniques. This is the fundamental procedure for determining the indicator's weight and consistency ratio. This is a tabular column of SATI's scale of relative importance. These are the steps involved in calculating consistency ratio, and consistency index was shown. In these results, the figure 4 shows the slope map of the area. Red color indicates the higher the slope and the blue color indicates the lesser the slope. In the soil map, clay and clay loam soil are present in this area. In the figure 5, the annual average mean rainfall map was shown. Dark blue color shows lesser rainfall and light blue color shows more rainfall. Drainage density map was generated using kernel density to calculate the drainage density area from stream polyline features. Land use land cover map shows that variation in the land use like water, barren land, vegetation, settlements and the cropland area. In the flow length map, the blue color indicates the higher flow length and red color shows lesser flow length. Lastly, the flood hazard map was generated by using all these criteria. In this map, the flood hazard area divided into 5 parts: very low, low, moderate, high and very high risk of flooding. Brown and dark red color shows the very low and high risk of flooding zones respectively. And the flood hazard map was exported. In this study, a flood hazard map for the specified region was created by using GIS techniques. Various factors like slope, drainage density, and few more maps were considered. Analytic hierarchy process analysis assigned weightages to each factor, and raster weighted analysis produced the final flood hazard map. The findings reveals that 18.79% and 21.81% of the area are highly and very highly prone to flooding. Emphasizing the need for precautionary measures, only 26.35%, around 8.7 square kilometer of the study area deemed safe from potential flooding events. These are some of the references which we considered for this work. Thank you for giving this great opportunity. Thank you one and all.
The IMD data you have used is from which year to which year, and how many stations did you take? Okay, for only that particular year. Or just okay, okay. Okay, thank you.
I have a question, sir. So you have mentioned one of your parameter as river distance. So river distance, yes. So I can understand you are actually putting some weightage like the place is how far from the river. So my question is, if a place is in between two river streams, so how you are going to define the weightage of this place? There can be two or more river streams, like, yeah. Okay, you are considering the primary river only. Okay.
Thank you very much for this nice presentation. I have just a curiosity. You have obtained a risk map at the end. Which is the objective of this risk map? Is to offer them to the authorities, or is just come out from a research project? Which is the objective to create this risk map? Yeah, I mean, what do you want to do with the map you are obtaining? Do you want to deliver this map to the authorities just to prevent people? No? Okay.
Do you have any historic data about actual flood events to confirm your results that you established with your risk map? So could you look into past flooding events if the areas that you identify as high risk areas are really those areas that are flooded? Is there any data available in India? Okay, so you can compare your risk map with the actual flood map, and that coincides. The risk areas that you identify are the same that are flooded at the end, or you don't know yet if this, okay.
So I was curious if it is a predictive risk modeling or this is after the fact. The disaster has happened. Okay, this is after the fact. Do you plan to extend this research to do more predictive modeling so that if the event is, if there's a rainfall and stuff event is about to happen, you do have the map of the previous flooding?
We move to the next presentation, characterizing water dynamics of coastal aquaculture ponds using pixel-based time series analysis.
Good afternoon to one and all. Myself, Prakash from Central University of Tamil Nadu, Tiwari, and I am going to present my work about characterizing water dynamics of coastal aquaculture ponds using index-based time series analysis. Since the 1970s, global aquaculture production has gained its importance with the rapidly growing world population. Although an increase in aquaculture production is expected in all regions and the largest expansion is expected in India during the time period of 2010 and 2030. This rapid increase of aquaculture production in India led to uncontrolled and unsustainable conversion of such coastal wetlands, particularly mangrove to shrimp cultivation pond in recent times, which raising concerns among the climate scientists, environmental managers, and policymakers regarding the impact of aquaculture system on prevailing coastal ecosystem. So the accurate monitoring of water presence in aquaculture pond is very crucial for health, productivity, sustainable management, and competent decision making in the coastal aquaculture pond. The study was conducted in 72 taluks of Tiwari, Nagapattinam, and Tanjore districts of Tamil Nadu along the coast of Bay of Bengal, and it forms the southernmost part of the coastal Kaveri Delta. The study area was mainly engaged in shrimp farming due to its low topography and proximity to wetlands and river estuaries, which plays a major role in the coastal aquaculture production. The methodology involves the following steps. Firstly, the coastal aquaculture structure was extracted manually in the QGIS using Sentinel-1 SAR data with the Google Earth Engine plugin from the year 2017 to 22. The Sentinel-1 SAR data used because it is help us to identify the pond structure and boundaries more effectively. And secondly, to analyze the water extent, normalized difference water index NDWI was calculated in the Google Earth Engine platform by using the Sentinel-2 data. To understand the seasonal inundation dynamics and to avoid the misinterpretation of inundation originated from monsoonal precipitation, we extracted season-wise NDVI for the season winter, summer, southwest monsoon, and northeast monsoon. By using the NDVI season-wise data, we prepared water frequency map, which gives us the spatial distribution and frequency of water occurrence over a period of time. By amalgamating the data over various seasons, the map shows us areas where the water body is permanent or seasonal. The water frequency map was classified into 5 classes like 0%, 25%, 50%, 75%, and 100% from the year 2017 to 22. Then the water frequency map was overlaid with the manually extracted aquaculture pond with the respective years. Then a zonal statistics was performed to calculate the mean value for water pixels, which falls within each aquaculture pond. The pixel mean value of coastal aquaculture gives us average pixel intensity encompassing each pond, and that give us information about dynamics of water presence in the coastal aquaculture ponds. Using the mean values, the coastal aquaculture pond were classified into 10 classes like 0 to 10%, 11 to 20%, 21 to 30%, and like till 90 to 100% based on the presence of water in it. Then finally, NDWA pixel-based time series analysis are performed because pixel-based time series will help us to analyze the temporal trends and patterns within each pixel over a period of time. To extract the pixel-based time series NDWI, stratified sampling procedure was followed by taking the time series NDWA value for 3 classes based on water frequency, namely very less, that is 0 to 10%, then 41 to 50%, which comes under moderate, and very high, which falls under 91 to 100%. Then the obtained pixel time series data of 2018 and 22 was averaged year-wise, and it was used to interpret the seasonal dynamics. And the results we got are, we observed a positive trend in coastal aquaculture growth from 2017 to 22 in the overall study area. The count of coastal aquaculture ponds was 6,112 in 2017, and it was steadily increased to 6,220 in 2022. This positive trend clearly indicates the establishment and expansion of coastal aquaculture pond over the period of time. Because due to its flat topography and favorable hydrologic conditions, this area provides suitable place to install coastal aquaculture farm. Another important results are the coastal aquaculture ponds with the higher percentage of water presence were shifted from Talina region towards the Muktapet region between 2017 and 22. In these two maps, we can clearly see the shift between the both regions. Then the water frequency map also indicates the shift in magnitude of water presence, where the magnitude of water was higher in Talina region and during the 2017, and it was lower in 2022. Then in the pixel-based time series, like we got the results like the pixel-based NDWA time series value for the classes 0 to 10 shows the values varies between minus 0.1 to minus 0.35, which indicates the presence of lesser water. In both the years, the dryness fluctuates between summer and southwest monsoon in 2018 and 22. In 41 to 50% class, the NDWA time series value varies between minus 0.1 to 0.25 in 2018, and in 2022 it varies between minus 0.05 to 0.05, which indicates the presence of moderate water in aquaculture pond. It hits the peak during the northeast monsoon in 2018, and during the 2022 water presence was maintained in summer and northeast monsoon. In 91 to 100% class, the values varies between 0 to 0.40, which indicates the ponds which moderate to high level of water presence, and it shows that pond is consistently underwater. So by the conclusion, the result shows the prominent shifting in coastal aquaculture activities from Talina region towards the Muktapet region between 2017 and 22. Further, the adopted methodology clearly showed the pixel-based time series of NDWA change would be effective to understand the intensity of shrimp farming and working condition of the existing ponds. Also, the results of the study will be helpful for stakeholders and policymakers to frame suitable management practice to achieve the climate resilient, sustainable coastal aquaculture. So we finally thank ICSSR for their financial support to conduct the study throughout the manual project. Thank you.
If I followed the presentation correctly, you're identifying the extension of these ponds based on the normalized spatial expansion of this pond. So are you sure that the water level of these ponds, when they are spatially extended, will be same for the same season, or do you see any differences in the season? Yeah, level of water in each individual pond in the same season. Your NDWA values will be changing for each individual pond, not dependent on the season.
Thank you. Any other question? No? So if not, we're going to move to the next one. Thank you very much.
So the next presentation will be on hydrological implications of land use, land cover changes in the Netravati River Basin, and will be given by Shantana S or Shantana M.
Hello all, I'm Chandana, MTech student from the National Institute of Engineering, Mysuru, here to present my presentation on hydrological implications of land use land cover changes in the Netravati River Basin, insights from the SWOT modeling and machine learning techniques. Water is a universal renewable source which are of different forms. As rain, it falls to the ground and flows. That has been depleting quantitatively and qualitatively. The variations of the flow, which impacts in the flood drought, furthermore for the water scarcity, the available surface water is of 1%, which is affected by the land cover classes. The elements of the water cycle like precipitation and temperature plays an important role. Thus, monitoring this is an important part, which can be carried out using the hydrological model, such as soil and water assessment tool. Further, for the time consumption and for the multiplicative processes, these machine learning techniques were introduced, in which supervised classification, which classifies with respect to classification and a regression model. In that, RF, SVM and ANN methods were utilized. Basically, RF works based on the decision tree and the majority of that with respect to the output. This can be of a bagging and a boosting methods, in which the bagging says that review and keep your results, and furthermore, for boosting it is that review and reuse the results. SVM creates a margin for the identities, for the separation of the identities, and ANN, as similar to the human brain, it performs with respect to the known input and output parameters for the provided output constraints. Thus, the objective of the study is to obtain the land use land cover change analysis and its effects on the stream flow, and to stimulate the stream flow using the hydrological model. Further, to obtain the stream flow prediction using the machine learning techniques and to evaluate those models. This study focuses on the improvement in the stream flow prediction, and it can be a valuable tool for the water and hazard management throughout the stream flow forecasting. Therefore, the Netravati catchment of the Dakshin Kannada, Karnataka, which covers an area of 3,657 km², which has the longest river path of 107 kilometers, drains across the catchment with an hydroclimatical station Bantwal has been located in our study area. Apparently, the collection of data sets were carried out using the conventional and remote sensing method with respect to their purposes. Coming to our overall methodology, it has 3 different ways and its tool. In change detection, the land cover analysis and LSD was carried out using the freeware Google Earth engine software, and the land use land cover analysis was carried out using the random forest algorithm, and LSD was estimated using the split window algorithm. SWOT analysis was carried out with the input parameters as hydrological and climatical and station data to be an input parameter, and to know the watershed and a sub-basin and creation of HRU to obtain the flow, and to analyze the observed flow with the obtained flow and validate it. Furtherly, for the machine learning algorithms, the R programming language was utilized for the RF, SVM and ANN, and for the evaluation of those models and for the intercomparison of those. LULC results on deforestation of 7.34 and the class buildup has been risen with the 3.19% of the areas, which has been visualized with the training and testing datasets performances from 2000, 2018 and 2020-22. Coming to the land surface temperature analysis, the rise of 2.98 degrees Celsius for the study period has been noticed, wherein the rainfall runoff model was estimated, which has been presented with a time series plot for the Bantwal station, also finds the decreasing trend. Now, the stream flow prediction using the hydrological model and a machine learning model has been plotted using the 1:1 plot with its under-prediction and over-prediction results. For all the actual and the stream flow prediction, the ANN outperforms the other model with the R-square of 0.94. Extending our analysis with the training and testing datasets for each of the model with R-squared, RMSE, MAE and NSE, whereas R square greater than 0.85 and NSE greater than 0.7 is considered to be good and acceptable results, in which ANN satisfies its performance with the best results. All in all, the land cover classes plays an important role towards the surface runoff. Majorly, the build-up and deforestation is visualized from 2000 to 2018, whereas the class dense shows a negative correlation towards the surface runoff, and with the increasing class build-up, the surface runoff will be more. As of the ANN performs with higher accuracy, which can be a valuable tool for hazard and water management. Further, our study will be extended with a comparative study for the other machine learning models with the identification of the best model. Finally, I would like to thank all the stakeholders for providing me the datasets and the support to completion of the study. These are our selected references which have been presented. At last, I would like to thank all of you for providing me this opportunity to present my study here. Thank you all.
Thank you for the nice presentation. Are there any questions in the room? And I have a question. Which runoff data did you use? Runoff data, you compared to runoff data in your conclusions. You had, which runoff data did you use? On the river, basically. Okay. Okay, I think I understand. Yes. Are there other questions? Then we move to the next speaker.
Thank you very much. Now we are moving to the 49, groundwater quality evaluation in the Gurupura River Basin using GIS and remote sensing approach by Villar, Surya, Wanshi, or any other author of this paper.
Hi everyone, I'm Kuku Sara, research scholar from IIT Bombay. Today my topic of presentation is analyzing the diurnal evolution of land surface temperature during heat wave event at high spatial resolution. So over the past few decades, the frequency of heat waves has increased significantly. This could be more likely due to the human-induced climate change. Traditionally, heat waves are declared and monitored using air temperature observations at several meteorological stations. But the scarcity of weather stations and non-availability of continuous data are a major drawback of using these air temperature data. Whereas LST from thermal infrared sensors or land surface temperature from thermal infrared sensors provide continuous data. It represents the temperature of the surface, and the surface can be vegetation, soil, concrete, or anything. As you can see from this figure, the LST varies over the course of a day, and therefore this diurnal temperature cycle is crucial in understanding the thermal characteristics of a land surface. And this knowledge can be beneficial for understanding plant water needs, mitigation strategies during an extreme heat event, etc. Generally, geostationary satellites provide 15 minutes or 13 minutes data throughout the day, but they are coarser in resolutions, limiting its application use in many applications. Whereas polar orbiting satellites are much finer, but acquires the data maximum twice a day, which is not enough to generate a diurnal cycle. Hence, we developed a hybrid model combining disaggregation and diurnal temperature model to generate a field scale LST and its diurnal cycle. So using this model, we have studied the variation of diurnal temperature cycle of different land cover types in 2 geographical locations in India where heat waves were reported frequently. First one is Bathinda. So this is one of the districts where a significant decline in the wheat production was observed, attributing to the onset of a heat wave in 2022. And second one is Jalgaon district in Maharashtra. So over these 2 sites, the DTCs of different land cover types were compared for a warmer year and a cooler year. So the data sets used for the study are MODIS LST images, that is the 4 images acquired per day using from the Terra and Aqua satellites. So whenever the MODIS data was not available, VARS data was used. And so we are going to downscale the MODIS LST at 980 meter spatial resolution to 70 meter. So for the downscaling process, several auxiliary variables were also used. That is Sentinel-1 VV polarization, then topographical data from SRTM DEM, and several indices from the reflectance bands of Landsat 7, 8, 9, etc. The methodology is given here. So all the auxiliary variables were upscaled to 980 meter and they were converted into principal components. Then the multilinear relationship was established between the LST images and the principal components at 980 meter. Then this relationship was applied to the fine resolution principal components at 70 meter to predict the fine resolution LST at 70 meter. So per day, 4 images were predicted at 70 meter. So these 4 images were fitted to derive a diurnal cycle using the GOD-SURA-1 TS DTC model, which is a semi-empirical model. Which has few parameters that are calculated using a minimization technique, and the DTC were fitted. So coming to the results, so in order to identify the warmer year and a cooler year, thermal anomaly maps were prepared. So thermal anomaly maps are nothing but the deviation of temperature from a long-term mean. So for the Jalgaon district, 2019 and 17 was considered as identified as warmer year and comparatively normal year. And these are the all the images over these 2 years were downscaled to 70 meters. So the downscaled images are shown here. So we can see that in the year 2019, most of the pixels are very warm compared to 2017. And especially during night, we can see that the urban pixels are warm. So this could be indicative of urban heat island effect. Similarly, their diurnal temperature cycles were also compared for both these years. So as we can see here, minimum temperature and maximum temperature were pretty high for 2019 compared to 2017. And also if we see the temperature amplitude, that is the difference between the maximum temperature and minimum temperature. For the cropland, there is a significant increase in the temperature amplitude in the year 2019. This could be due to vegetative stress. And also, if we see the time at which maximum temperature was reached, the peak has reached pretty earlier for the year 2019. Similar analysis was done for the Bathinda district also. So to here, 2022 and 2020 were identified as warmer year and comparatively cooler year. And these are the diurnal temperature cycle comparison. So here the temperature variations throughout the day for 2022 was pretty higher compared to 2020. So this image here helps to understand the significance of a high resolution imagery. So figure A represents the Landsat 8 LST image at 70 meter. And B and C are a zoomed in version of a small region represented by this red square here. So B is the Modus Terra LST image at 980 meter and C is the downscaled LST at the same time at 70 meter. So here from this figure B, we can identify that like all the hot pockets in the downscaled images are being averaged out in the Modus LST. So if we see the DTC cycle for at the points P1 and P2, we can see that at P1 the higher temporal variations throughout the day was missed by this modus data, whereas downscaled LST was able to capture those temporal variations. So it is very important to have a high temporal resolution image where over a heterogeneous land surface for analyzing the diurnal variations there. So coming to the conclusions, the temperature and duration of heat anomalies can vary for different land cover types in the same region. LST can be, along with air temperature, LST can also be used as a proxy with heat stress index to monitor and mitigate the heat events at a finer scale. Identifying hotspots and time at which temperature peaks can help in mitigating the impacts of heat waves. Like I said previously, the vegetation stress can be identified, and when to water the plants can be decided. Also, in case of urban heat island, where to incorporate the green spaces can be decided using these informations.
Actually, you are showing different images for different years, no? So, no, that kind of like time series, like 2017, 16. So I am asking, like, you are taking like some images and like calculating the mean or median, or then analyzing or a particular day event like that. Okay, that entire data is for a range of data, no? Median or mean, like that's something mean. You are taking mean. Okay, how you can filter out the seasonality or any other parameters? Okay, only for that particular, for Bitinda Punjab. So only for that particular geographical area you are so like extrapolating.
Any other question?
I didn't fully understand how you derived some downscaling weights factors based on a range of different parameters. How did you derive these downscaling factors, or which method did you use to derive them?
Also, Landsat 8 and 9 have the TIR band, thermal band. Then why use the MODIS only? MODIS has a coarser resolution than the Landsat, and Landsat is also more sensitive toward the agriculture or vegetation than the in contrast of the resolution. So my question is, why you not consider the Landsat for this particular things? Can you compare that result with the in a month or a 2-month periods with the Landsat? I understand, but my question is the diurnal cycle. It means if you can take 2 months or 3 months, just like April or May, can you compare with that result with Landsat or not? No, 1 year you taken May or April or May. Okay, so 2-month data of MODIS, can you compare with that Landsat or not? Yeah, with TIR.
Good morning everyone, I am Aparna from IIIT Mohali. Today I will be presenting my work, SBAS InSAR analysis of coastal subsidence in Kerala, India to monitor flood inundation risk due to relative sea level rise. The motivation behind my work is the flooding in India. If you look at this graph, you will see that India tops the world for the most number of deaths due to floods only in the year 2022 with more than 1,000 deaths. If you look at the past years as well, India has faced a lot of deaths due to floods. And one of the most devastating floods that India has ever witnessed was the Kerala floods of 2018 with more than 400 reported deaths and a huge economic loss. Although flooding is my motivation, I am more interested to look at the coastal subsidence and the sea level rise scenario in Kerala and to come up with a flood inundation map for the future. So these are my objectives. Assessment of coastal subsidence in India using multi-terminal interferometric synthetic aperture radar technique, and also a prediction of flood inundation in the year 2100 by including the factor of sea level rise and vertical motion. These images depicts the situation of Kerala floods of 2018. A quick background about my study area. The digital elevation model of Kerala shows that towards the coastline, Kerala has a lot of low-lying region with an elevation of less than 20 meters above sea level. Here is a rainfall pattern of Kerala. It shows that during the year 2018 and 19, Kerala has received a heavy rainfall during its monsoon seasons of June, July and August. And the language land cover changes during the year 2018 to 2022 shows that towards the coastline we have a lot of built-in area which is marked in red color. We do have a tidegate station in Kochi Willingdon Island. The data from the tidegate station shows that there is a relative sea level trend of 1.90 millimeter per year in Kerala, and NASA has projected the sea level changes to the year 2140 and above. And according to the socio-economic scenario SSP 37.0, which is a medium to high reference scenario, by the year 2100 we expect a sea level change of 0.71 meter. So my idea was to incorporate the sea level rise changes and also the vertical land motion derived from the INSAR results to come up with a flood inundation risk assessment map. So this is the methodology that we have used for mapping the coastal subsidence, multi-temporal synthetic aperture, interferometric synthetic aperture radar. So this is the idea of INSAR or interferometric synthetic aperture radar. So when the satellite passes through the same region over two different time periods, if there is a subsidence of the land or deformation of the land, then there will be a phase difference between these two satellite passes. We make use of this phase difference to generate the interferogram and to look at the vertical land motions. So these are the various steps involved in anti-INSAR processing: co-registration to align the images, interferogram generation by subtracting the phase values, filtering, we did Goldstein filtering, and phase unwrapping, we have applied the SNAP algorithm, and SBAS inversion to obtain the displacement values from the phase values. Here is the data used. We have used a huge data of 1.4 terabytes. It is the Sentinel synthetic aperture radar data during the years 2017 and 2022. We have used two satellite paths. As of now, we will be showing the results of path number 165 only as a preliminary results. And we have also used a lot of auxiliary data like the time course data, the land use uncover data, rainfall data, and digital elevation model. Here is the workflow. So first we got the line of sight velocity from the INSAR processing, and we convert it into vertical velocity by applying simple unit vector projection. So this results from the vertical land motion, and also the sea level rise data is used along with the digital elevation model to come up with the flood inundation map. So here are some of the results from anti-INSAR processing. We have processed the southern region, southern part of Kerala. It shows that most of the regions are slow subsiding with a velocity of more than 5 millimeter per year. But if you look at this closely, there is a significant subsidence in some of the regions, especially in Kutanad region of Alappuzha district, and also this is Kochi region of Ernakulam district is showing a quite significant subsidence of more than 20 millimeter per year. Here is the inundation map that we have generated by considering vertical land motion, sea level rise, and the low-lying areas. So these are 6 different districts of the southern part of Kerala. More than 50 kilometers square area of all of these districts are prone to inundation due to a relative sea level rise in the year 2100. Thank you.
Thank you, Aparna, for the nice presentation. Are there any questions in the room? Any SAR interferometry specialist? Right, one.
See, you said 5 millimeter per year. What may be the error due to atmosphere or some other errors? You can expect dam error. What are the errors?
Yeah, atmospheric error could be there. We haven't done the atmospheric correction yet. We are looking forward to that also. We have calculated the RMS error. It's about 2 millimeter per year, 0.2 millimeter per year to 2.6 millimeter per year, in that range. So there could be atmospheric error. We haven't done a correction yet. We have to do the APS correction, and we are doing that as well.
Okay, thank you. One more question here.
My question is like, how much reliable is this? Like, how did you validate the data? Because like subsidence, this differential interferometry, they can give like the phase will be changing if there is a huge erosion is happening. So Kerala will be having like huge erosional surface runoff 10 in that entire region, because that is a delta of 3 rivers in Kerala. So whether it is because of subsidence or neotectonics or due to this precipitation and meteorological erosional activity, did you calculate any surface runoff or surface erosion to validate this?
Yeah, so actually we do not have a GPS station in Kerala, so that we haven't, we have a limitation to do our data validation. And this area, the Kutnad regions are wetlands and also a low-lying area. So we could say that one reason for the subsidence, higher subsidence shown in this area could be due to the this wetlands, and also it's a highly flooded area, low-lying region, and an agriculture area. As of now, we haven't calculated these factors of surface erosion. This is an ongoing work. This is the preliminary results of this work, and we are still working on this to look at all these factors as well.
Okay, why I asked, because like subsidence is different, like erosion is different. So both will be giving like phase difference in long period. So that's why.
Some groundwater extraction, which could also lead to this.
Can you repeat what you said? I think we missed it.
Yeah, so we are looking at various factors as of now. So we are also looking at if there is some groundwater extraction which can lead to subsidence. So the result validation part, we are working on it. First of all, there is a lack of GPS station, but we will be looking at other factors also as a part of future work. So these are the preliminary results that we have used from we have got from our work.
Okay, thank you. Any other question? Okay, thank you, Aparna. We had one no-show. Is he maybe in the room, or she? The talk was on groundwater quality evaluation. Paper 49 from VI Surya Vanshi. No. Online? No, it's not online. Okay, then I thank you for joining this session. Thank you to all the speakers. I think it was a very nice session, very interesting results and very mixed results. And with this, I think we close the session. Thank you.